Alright, we should be back now. Let me do a quick sound check. Let me grab those headphones again. I don't expect that anything went wrong with the sound, but you never know. It doesn't hurt to double check that stuff. Let me plug this thing in and listen in on the preview. Okay, that all sounds good. Sound is working fine, and is video working fine as well? Yep, looks like it. Alright, put the headphones away. And let's get started with our topic of the day. So I decided for today the topic to cover would be Riemann sums because I feel like that would be relevant to my physics students. I've already discussed the basics with some of them, but it doesn't hurt to start over from the beginning. So Riemann sums. Riemann sums. What are they? How do we use them? Well, if you were here for the physics portion of the live stream, then you saw me argue that the area under the curve of a velocity versus time graph gives you displacement, and a lot of times you are going to be calculating areas, whether it's in calculus proper or in science courses that use calculus, primarily physics, but occasionally chemistry. So how would we deal with, so in physics I showed how you would calculate area under a curve when the quote-unquote curve is actually just a straight line. That's pretty easy. You just chop it into familiar shapes from geometry, triangles and trapezoids and rectangles and whatnot. But what if you actually have a function that looks more like this? Actually, let me think. Do I want to draw a random curve? Yeah, we'll draw something random for now. What if you have a function that looks more like this? How do you calculate the area between this shape and the horizontal axis? How do you calculate this area? Well, Riemann sums offer the solution. So the first thing we want to do is show how to approximate the area under a curve, and for that I actually want to draw a familiar graph, which is the graph of x squared. So let's draw a familiar looking graph. I think I actually want to do this in centimeters. I want this to go all the way up to at least 9, so yeah, 10 might be good for us here. And then I guess I'll do this, and let's see, I want it to go up to at least 3. Okay, something like that. And let me go ahead and start spacing all the different values. So 1, 2, 3, 4, 5. I could have just scaled the vertical axis differently, but oh well. I know that's what I did with one of my students. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then all the way up there should be 10. And then over here, I'll just do 1, 2, 3, and then 4 is going to be off of the page anyway, so I'm not even going to need to bother with it, but we'll mark it just for the sake of marking it. 1, 2, 3, 4. Okay, so if I were to draw the graph of x squared, it's going to have, I guess I'll do orange for this. It's going to have a point at, so if f of x equals x squared is what I'm trying to graph, it's going to have a point at 1, 1, and then it's going to have a point at 2, 4. Let me actually try and get this somewhat precise. 2, 4, and then it's going to have a point at 3, 9. And I think I want to actually use my ruler for this. Okay, and we're going to have a point at 3, 9, and it's going to keep going up and up from there. So let's see if I can draw this carefully and make it look good, make it look convincing. So 3 points to pass through. I think I messed it up already. Okay, that's about as good as it's going to get. Something like this. Okay, so there's our graph of f of x equals x squared. And we want to calculate the area of this graph at least between 0 and 3. We want to calculate the area of this graph on the interval 0 to 3. So that's the first thing that we need in order to calculate a Riemann sum. First, we need to know what is the interval over which we are calculating the sum. So our interval, we say the starting value of our interval is a, and the ending value is b. In this case, it would be from 0 to 3. That's the interval over which we are trying to calculate the area. So we are trying to get, I want to use a lighter color for this, so I'm going to do orange actually. We are trying to get this area. I'm going to try and not draw too darkly under it. We're trying to get the area of this shaded region. And we don't really have a simple formula for it from geometry. But what we do have a simple formula for is a rectangle. What do rectangles have to do with this? Well, if I chop this area up into a bunch of little rectangles, then I might be able to get an approximation for the area over here. Now, depending on how I choose the heights of these rectangles, I might get an underestimate or an overestimate or something in between. But no matter what I'm getting is an estimate. So there are 3 different rectangle rules that we tend to use when trying to approximate areas under the curve. We have a left rectangular approximation. Well, first of all, let me define. RAM stands for rectangular approximation method. RAM. Rectangular approximation method. We've got three different approximation methods involving rectangles. We've got the left rectangular approximation method. We've got the right rectangular approximation method, and we have the midpoint rectangular approximation method. That is a little too close for comfort. Those are the three different rectangular approximations, and we'll go over the meaning of them using that first graph actually, because I don't want to draw too much over this second graph just yet. So left rectangular approximation, let's say I want to do it over the interval from here to here. Let's say this is my A and this is my B, and I want to approximate this area, this little chunk of the green shaded region between A and B using rectangles. Well, I have a couple of options in how I want to draw my rectangles. I could draw my rectangles such that they rise up until they hit the curve on their left end. So I could draw my first rectangle over here like this. And then my second rectangle would be drawn right next to it, where it rises all the way until it hits the curve on its left end like this. And then I extend it for whatever width I decided. Bring it down, and then my next rectangle, same thing, hits the curve on its left end. Next rectangle, same thing. Next rectangle, I guess its left end would be all the way up here at the peak. And then it comes down like that. And I could calculate the areas of each of these individual rectangles. And what I would find is, well, this rectangle is an underestimate because it's missing that little bit of green that's sitting above it. This one's an underestimate. This one's an underestimate. This one's an underestimate. This one is an overestimate because you see that the last rectangle actually goes a little bit outside of the bounds of the curve. So left rectangular approximation on a curve that's generally going up tends to underestimate the area under the curve. What about a right rectangular approximation? Let's pick a section where, again, the curve is mostly rising, and you'll see it'll have the opposite problem. So let's pick another interval. Let's say it's from C to D. Let's pick an interval over here, for example. And let's see what right rectangles look like. So a right rectangle, if I divide this into sections, let's go ahead and actually pre-divide them like this. Then what I want to do with each rectangle is I want its height to be determined by its right end hitting the curve. So the right end of my first rectangle is going to go all the way up to here. So my first rectangle is going to look like this. Next rectangle's height is going to be determined by its right end hitting the curve over there, and so on and so forth. And you can see when the graph is going up, usually the right rectangular approximation method tends to overestimate the area because you've got a lot of bits of rectangle hanging outside of the boundaries of the curve. And then our last rectangle is also an overestimate over here. And so the midpoint rectangular approximation method tends to be the best of both worlds. It tends to have the least error because it kind of strikes a balance between the two. It has a little bit of underestimate, a little bit of overestimate. I'll draw a separate curve for that. Let's draw another graph, and this time I'm not going to use the ruler. I'm going to make it a little crude, but I think it'll still be good enough to drive the point home. So let's draw another random curve, let's say something like this. And let's go ahead and pick an interval on here. Let's say from here to here. Well, I guess that, hold on. You know what? No, scratch this. Let's do it. Let's make this the A, and let's make this the B. Yeah, that looks a little bit better, because this one is practically a rectangle already. Not really the best way to illustrate my point. If I were to use the midpoint rule, I want to make it a little bit easier to see, so I think I'm going to use wider rectangles for this. I'm just going to cut this up into 3 rectangles as opposed to the 4 or 5 that I did over there. So midpoint rule would be I take the left end and then I take where the right end of my interval would hit the function, and then I just take whatever is in between those two. So right here, somewhere between those two, somewhere between f of a and f of whatever you want to call this, halfway in between, that's what I would use as the height of my rectangle. And I guess this one is mostly over and outside of the curve, but if I take a look at the next one, we've got a function value here and a function value here, and then halfway in between those two would be something like this. Okay, with this it's a little bit more clear that it has a little bit going outside of the curve, a little bit of overestimate in here, but also it underestimates the curve by a little bit over here. And these areas are by no means equal, but it's better than having just a blatant overestimate with no underestimates mixed in. It gets you a little bit closer to an accurate approximation if you have some underestimate mixed with some overestimate. Let me draw the final one. Our final one actually is already pretty much at its midpoint. There's barely any, yeah, it's pretty much flat over here. So I guess this one, it does have a little bit of overestimate there and a very microscopic underestimate that we can't even see with the naked eye. But yeah, if you were to calculate the areas of each of these rectangles, you'd get an approximation for the actual area under that curve. So those are the 3 different rectangular approximation techniques, and there are other approximation techniques. There's actually a technique where you use parabolas, where you take a curved area and you approximate it using parabolas that you can fit inside of it. And I won't go over that, but just a quick illustration of what that would look like. Once you learn how to calculate the area under a parabola, if you have a curve that looks like this, you can fit parabolas into it. Because, I mean, look, you can fit this parabola in here, and then you can fit a parabola in here, and yeah, all sorts of polynomial functions can have parabolas fitted into them that might lead to a more precise approximation depending on the original shape of the curve. You can also approximate using trapezoids, although it tends to be less accurate than just using midpoint rectangles. You could, for example, here, if I wanted to take this interval, for example, from here to here, so I'll call that C and I'll call that D, I could cut this into trapezoids, and not the isosceles trapezoids that you might think of at first when you hear the word trapezoid, not these trapezoids, these kinds of trapezoids that have a flat side and then a sharper side. You could use trapezoid approximation, which at first looks like it might be more precise just because the shape of a trapezoid tends to slant up with curves that curve upward and slant down with curves that slant downward. But people who are better at math than me did the work, and they were able to demonstrate that the amount of error in using the trapezoid as your shape for approximation is often bigger than it is when just using midpoint rectangles. So midpoint rectangles are probably the best way to go. Although in calculus, once you make your rectangles really thin, the more of these rectangles that you can stuff into an interval, the thinner they are, the thinner these little errors are. And eventually, if you make them so thin, the differences between left, right, and midpoint start to vanish. And at that point, they all effectively lead to the same results. Anyway, let's go ahead and try and approximate the area under this parabola using the midpoint rule. I will tell you in advance that the area over here using calculus would be, let's see, 1/3 times 27 would be, this area should be 9, right? Hold on, 1/3 times 27 minus 1/3 times 0, yeah, should be 9. So the area over here, area should actually be exactly 9 if I did this correctly. Let's use the midpoint rule for this to try and approximate this area. So I'm going to cut this into 3 rectangles because we don't have all day. I'm going to cut this into 3 rectangles. Well, actually, let me ask first. What if we just approximated this as 1 rectangle with a height of 9 and a width of 3? Then we would be severely overestimating this area as 3 times 9, 27. What if I increase the number of rectangles from 1 to 3? So I wanted to do, let's see, f of 1 is 1 and f of 0 is 0. So halfway between 1 and 0 is 1/2. So this thing has a height of, I'll write it as 0.5, and a width of 1. All of my rectangles are going to have a width of 1 because that's just how I chose for it to be. You can vary the widths of your rectangles if you want to, but traditionally you are better off just keeping them the same width because it allows you to factor out the width of the rectangles and multiply by the sum of the heights of your rectangles. So I've got 1 times 0.5, and then next we've got, well, we already said f of 1 is 1, f of 2 is 4. Halfway between 1 and 4 is, let's see, 4 plus 1 is 5, divided by 2 is 2.5, so here. So this rectangle has a height of 2.5. And then our last rectangle, let me actually draw my second rectangle. Whoops, wait a minute. Oh no, I drew it in the wrong place. No, I didn't draw it in the wrong place. For a minute there I thought I did. Okay, that's my second rectangle right there. Has a height of 2.5. And then for my third rectangle, we've got 4 and 9. And then halfway between 4 and 9, 4 and 9 is 13. Divided by 2 is 6.5. So somewhere over here would be the height of my rectangle. And there we go. That's a rectangle with a height of 6.5. 6.5. Okay, let's calculate that total area. So total area, this is my midpoint rectangular approximation, is equal to width times height, so 1 times 0.5 plus 1 times 2.5 plus 1 times 6.5. Notice, since I kept the widths of my rectangles the same, I could factor out the 1. I mean, it's a 1, so it's not going to make that much of a difference here, but if it was anything other than 1, being able to factor it out makes a huge difference, especially when you have way more than 3 rectangles to work with. So I'm going to just go ahead and write the 1 factored out, even though it does seem kind of silly to do it when it's just a 1. And add the sums of the heights. Add the heights together and multiply the sum of the heights of my rectangles by their common width. 0.5 plus 2.5 is 3, and added to 6.5 is going to be 9.5 is our approximation for the area. The actual value is 9, so there is clearly some error in doing this, but that error can be significantly reduced if you increase the number of rectangles. If I were to hypothetically come up with a way where I could have an infinite number of rectangles, then I could minimize the error all the way down to 0. And that's what calculus allows you to do. So let's go ahead and come up with a formula for this and see what math we can do with it. Let's come up with, I want to do a formula for, what do I want to do? I want to come up with a formula for, it doesn't matter once you've got infinite rectangles with very little width. Like I said earlier, the differences between these 3 approximation methods starts to vanish. Which one would be the most convenient for me to use then, in terms of just writing a general formula for this? Well, actually, let me go ahead and just write a basic formula for this one. So I want to use the summation symbol. So we have basically the sum of 3 rectangles. We've got the sum from I equals 1 to 3 for 3 total rectangles. We've got essentially f of, I guess I'll call it f of xi times the width, which is going to be a small change in x. I'm going to call that delta x. And my f of xi over here for the midpoint RAM is defined as, let's see, f of xi is the height of my rectangle, and that's going to be equal to, I guess it would be, let's see, so we have our starting value is 0. Hold on. So this is over the interval 0 to 3. So a equals 0, b equals 3. That's going to be a part of our formula here. Let me slow down and think carefully about how I want to write this. So it's going to be the first value is a itself, the next value is a plus 1, which is 1, the next value is a plus 1 plus 1, and the next value is a plus 1 plus 1 plus 1, which also happens to be equal to b. I guess we can leave the b out of it. So I want to do, let's see, it would be f of a plus f of a plus delta x over 2 is my first term. Then my second term, oh, and times the width, so times delta x, plus f of a plus delta x, f of a plus delta x. I should have started this somewhere higher. Plus f of a plus 2 delta x all over 2, and then times delta x. So we've got f of 0 plus f of 0 plus 1. That's what we did for the height of our first rectangle. F of 0 plus f of 1 divided by 2 multiplied by delta x, which is 1. And then f of 0 plus 1, so f of 1 plus f of 0 plus 2 times 1, so f of 2. F of 1 plus f of 2 over 2, that's our 2.5 times delta x is 1, and then plus f of a plus plus 2 delta x plus f of a plus 3 delta x over 2, and then all times a delta x, which I don't have the space for. I guess I'll write it out here, delta x. Yeah, that's not very legible, but hopefully following the pattern of those first two terms, you can see what this third term is supposed to be. Okay, so now I think I can rewrite this in a more in a slightly more expanded format. I can write this as, let me switch colors. I can write it as the sum from I equals 1 to 3 of f of xi is defined as f of a plus, well, the first term is going to be just a itself, so plus how many delta x's? No delta x's, so plus I minus 1 delta x plus f of a plus I delta x over 2 all times delta x. Okay, not the best looking formula, but I think you can follow it. So when I equals 1, this is f of a plus 0, exactly what we got here. And then plus f of a plus 1 delta x, that's exactly what we got over here. So this is again for I equals 1, and then the rest plays out the same. If we do I equals 2, f of a plus 2 minus 1, so 1 delta x, and that's exactly what we have here, plus f of a plus I equals 2 right now, so 2 delta x, and that's what we have right here. So yeah, it works. It's not very fun looking is the problem, so let's take advantage of the fact that when this number over here becomes increasingly large, the left, right, and midpoint approximation methods start to give us the same values. The differences between them start to vanish. Let's go ahead and do a Let's see, would left or right be better in this case? I think I would rather go with right. So let's go ahead and do that on the other side of this page. So I'm going to draw something over here. Just draw myself a curve. Should I make it an x squared curve? Sure, why not? This time I'm not going to be super detailed with marking my axes. Just the general shape of an x squared curve. There's my x-axis, there's my y-axis. If I wanted to do right rectangular approximation, wait, what color pen am I holding right now? I think that's the navy blue. I was about to toss it because I thought it was the black marker. Well, I mean, I guess I'm already holding a different color. Anyway, if I do right rectangular approximation, then that's my A, that's my B. Write down, how many rectangles do I want? Well, I guess I can just draw arbitrary rectangles here. Let's do 3 of them again, just for the sake of having a clear illustration. So right rectangles are going to look like this. That's approximately the same width across all 3. Okay, and then this one would look something like that, and then this one would look something like this. Okay, so those are my 3 rectangles there. This is a drawing with n equals 3 rectangles. So if I were to write this as just some sort of condensed summation formula like I have over here, I would do the following. So if we assume these widths to be even, then the delta x is going to be equal to, well, b minus a, right? The distance between b and a divided by the number of rectangles n. So that's a definition for delta x, which we will take advantage of later, but for now we're just going to keep our delta x written as a delta x while we write our formula. As for the heights of my rectangles, let's see, sum with I starting at 1 and going up to n for n rectangles would be f of xi times delta x. And what is our f of xi here? What is the height of each rectangle? The height of each rectangle starting at a, height of our first rectangle would be f of not a itself, but a plus delta x. Right? If this is a, then this over here is a plus delta x. And that's what we use for the height of our rectangle, f of a plus delta x for our first rectangle. So this is when I equals 1. When I equals 2 for our second rectangle, the height is 2 delta x away from a. So that's a plus 2 delta x, and the pattern is just when I increases, the number of delta x's that you add to a increases. And then when I equals 3, you can imagine that the height of the rectangle is f of a plus 3 delta x, and so on. So it looks like I can rewrite this as the sum, starting with I equals 1 up to n, of f of a plus delta x times I. I think I would rather write it as I times delta x. Yeah, you know what? Let me scrap this and let me try again over here. I equals 1 up to I equals n. We have f of a plus I delta x is the height, multiplied by the width is delta x. Okay, there we go. So that is our right rectangular approximation. This is our right RAM. Okay, what happens if I create so many of these rectangles that they become infinitely thin? What if the number of rectangles n approaches infinity? For those of you who have had calculus, you have hopefully heard of the concept of limits by now. I mean, it's the first thing you cover in calculus. So if I were to take the limit as n approaches infinity of this sum, what would I get? Let's do this for f of x equals x squared. We're going to have to derive some formulas, so this is going to take a while, but I think it will be worth it just to see that this doesn't just come out of nowhere. And by the way, what results from this expression is what we are going to call the integral from a to b of f of x with respect to x. You can think of this f of x as being the f of xi in our formula up there, and you can think of this dx as being like what becomes of the delta x as n approaches infinity. That might be helpful in just kind of making the intuitive connection between integrals and sums. Don't take it too literally, but I mean, that's kind of what dx is. It's a really, really, really tiny change in x. So this is what we're trying to arrive at. So let's go ahead and use f of x equals x squared and write out what this limit will be, and then we'll have to derive some equations that will actually help us evaluate the limit. So our limit as n approaches infinity from I equals 1 to I equals n of this expression. Well, f of a plus I delta x is just the square of whatever you put in here. This is for f of x equals x squared. For f of x equals x squared, f of this whole thing is just this whole thing squared. So it's going to be a plus I delta x squared times delta x. Equals limit as n approaches infinity. Maybe I should leave the n approaches infinity part out of it for the time being. I'm just going to rewrite the part inside the limit for now. A plus I delta x quantity squared times delta x is equal to sum from 1 to n of, if I FOIL this, I get a squared plus 2a I delta x plus, I guess that would be I squared delta x squared, and I'm going to put the delta x in parentheses when you square it, because technically without the parentheses it means something else. And then all that times a delta x. If I remember correctly, I still want to leave this delta x outside of the expression, but I might change my mind on that later. So one thing I can do with sums is I can split them into sums of different parts. So I can rewrite this as the sum from I equals 1 to n of a squared delta x plus the sum from I equals 1 to n of, what would this be? It would be 2ai, and I guess this delta x times this delta x is going to be delta x squared, plus the sum from I equals 1 to n of I squared, and then delta x squared times delta x becomes delta x cubed. The a's and the delta x's and this 2 over here do not depend on I, so I can factor them out of each of these sums. And in fact, I can make a simplification because my a here is equal to 0, so I can actually, I can take a shortcut here. So I can, let's do the factoring out first. So I can do a squared delta x times the sum from 1 to n of, I guess all that would be left here is 1, plus 2a delta x squared times the sum from 1 to n of I plus I forgot to factor out the delta x cubed. Let's scratch that and just write it down here. Plus delta x cubed times the sum from I equals 1 to n of I squared. Okay, there we go. So since our a here is equal to 0, I can go ahead and toss out this and this. Though if our a was not 0, then, this one would be easy enough to do. This over here would, if you want the sum from I equals 1 to n, you might remember this from pre-calculus. What is the sum from I equals 1 to n of I? Well, this would be 1 plus 2 plus 3 plus 4, all the way to eventually plus n. And you might remember that the trick to getting this sum is you do n plus 1 is equal to 2 plus whatever comes before n, 2 plus n minus 1, and so on and so forth. So all of them amount to n minus 1. So you do a bunch of pairs, n plus 1, n minus 1 plus 2, n minus 2 plus 3, all n minus 1s, multiplied by the total number of pairs, which is the total number of numbers, n, divided by 2. And that gives you the summation formula for, what do I want to call it? The summation formula for, I guess this would be an arithmetic sequence that increases by 1 every time. Actually, it doesn't even matter what the difference is. It will still... Actually, wait. No. Oh, and did I write a minus there? n plus 1 times n over 2. Actually, hold on. Would it matter if I doubled all of these numbers? If I did 2, 4, 6, I guess this would then be 2n and then 2n plus... Actually, you know what? Let's not think about it right now because it's not really our topic. I'll have to think about it later. Right now my brain is kind of fried. Maybe I shouldn't have done this after 3.5 hours of physics. But yeah, if a had not been 0 here, we could have still had to grapple with this, and what we would have done is substitute it with n plus 1 times n over 2. This we do still have to grapple with, so now let's try and figure out what the sum is of these squares. So let's try and figure out if there's a general formula for the sum from 1 to n of I squared. So this would be, of course, 1 squared plus 2 squared plus 3 squared, and so on, all the way to n squared. Let's see if we can get a formula for this. So something that is not always taught to people is that when you have a sequence like this that's based on some sort of polynomial, the degree of the polynomial is directly linked to the number of differences you have to take before the differences start to be equal. What am I even talking about? Well, let's take a look at this arithmetic sequence again. If I were to calculate partial sums, the first sum, if I go to n equals 1, I get 1. So let me do this in a different color. If I only went to n equals 1, then this sum would amount to 1. If I go to n equals 2, then I would get 1 plus 2, which is 3. If I then go to n equals 3, then I get 1 plus 2 plus 3, which is 6. If I go to n equals 4, I guess that would give me 10. And what you notice here is that the first difference is 2. From 1 to 3 is a difference of 2. From 3 to 6 is a difference of 3. From 6 to 10 is a difference of 4. Not surprising, right? I mean, we just added 2 and then 3 and then 4 to our first sum. That makes sense. But then you notice that the difference of the differences is constant. When the difference of the difference is constant, that tells you that you're looking at some sort of quadratic expression, which is exactly what we have here. We're looking at a second degree function. We're looking at n plus 1 times n over 2. If you just focus on the n's, you know you're going to get something having to do with n squared there. So similarly, we can make a guess as to what degree of polynomial this sum is going to be. If I go ahead and start writing partial sums, I've got 1 squared. My first partial sum is 1. My second partial sum, if I add the 2 squared to it, now it's 5, right? 1 plus 4 is 5. And next, if I add 9, I get 14. And next, if I add 4 squared is 16. If I add 16 to 14, that's 30. If I add, the next one would be 25, so that would be 30 plus 25 gives me 45. And I think that should be enough terms for us. So if I start calculating the differences here, let's see, I've got first difference is 4, then 9, then 16, no surprise there, then 25. If I start calculating second differences, I've got 5, and then 7, and then 9. Oh, and if I take a look at the differences between the second differences, I'm getting a constant 2. So my first, second, my third difference is constant. That tells me I'm looking at some sort of third degree polynomial. That tells me I'm looking at some sort of third degree polynomial. And maybe you're not too confident about this. I mean, I just got 2 numbers to be the same. What if I kept on going? Would I still see that pattern? And of course you would. Let's go ahead and add the next number. So after adding 25, the next number would be 6 squared is 36. 45 plus 36 would be 75, 81. Did I do that right? 36 plus 45, 70, and 11. Yeah, 81. Doing it 2 ways doesn't hurt. And then that would give us a difference of 36. I forgot my commas here, and here, and here. And then difference between 36 and 25 should be 11. And would you look at that, difference between 9 and 11 is also 2. So if you just kept going with this, you would still just end up getting 2s at your third difference. And those of you who know derivatives, you might be able to discover a relationship between the degree of a polynomial and this, and what this final number is, what this final number always seems to turn out to be, depending on the degree of the polynomial and the leading coefficient of that polynomial. But I won't say anything more on that. That's something you can explore for yourself. So I know that this sum must be some sort of third degree polynomial. So I'm going to express it as a n cubed plus b n squared plus c n plus d. Whatever this sum is, it must be some sort of third degree polynomial. And if we play around with this enough, we can figure out the values of a, b, c, and d. So if I go ahead and start with, let's see, if I start with, what do I want to start with? I guess we could start with n equals 0. With n equals 0, what is the sum over here? Well, there would be no sum. It would just be 0. So actually, wait, is it even appropriate to use n equals 0 here? I don't think so. Because this sum starts from I equals 1. Yeah, n equals 0 is not appropriate here. Man, I wish I started at I equals 0, but it's fine. We can work with it. Let's start with I equals 1. So when we have n equals 1, we get a sum of 1. So a times 1 cubed plus b times 1 squared plus c times 1 plus d is equal to 1. Then we've got when n equals 2, we get a sum of 5. So for n equals 1, we get 1. For n equals 2, we get 5. Let me just draw a line here so that I don't look below this top row. When n equals 2, our sum is 5. And when n equals 2, we get a times 2 cubed, so I guess that's 8a, plus b times 2 squared, so I guess that's 4b, plus c times 2, so that's 2c, plus d equals 5, and I guess I can go ahead and subtract these two equations to eliminate d. Next up, we have 14 is equal to a times, this would be when n equals 3, the sum is equal to 14, 1 squared plus 2 squared plus 3 squared. So in that case, we would get 3 cubed is 27 times a, plus 3 squared is 9 times b, plus 3c, plus d equals 14. And then we're going to need a fourth equation since we've got 4 unknowns. So next up, when n equals 4, 4 cubed is 64, so that's 64a, and then b times 4 squared, so that's 16b, and then c times 4, that's 4c, and plus d, and that should be 30. Okay, I think I'm going to need to start on a new sheet for this because this might take a lot of paper. And then we'll have to come back to this page to finally figure out that sum. Oh boy. I have a feeling I might end up screwing up some of the final steps anyway, even after all this work. But if that's the case, I'll come back later, maybe post a secondary video where I clean up anything that goes wrong during the live stream. That's the problem with teaching things live. You don't have the luxury of just kind of pausing and working on the problem on your own and making sure that it's all right. I probably should have just practiced it ahead of time, but I didn't really have the time for it, so we'll see. Mistakes might appear. So first thing I want to do is, well, I can eliminate d no matter which of these equations I use, so I can reduce this to 3 equations not involving d pretty easily just by subtracting the first equation from each of them. So I think that's the first thing I'm going to do. I'm going to go ahead and first off switch colors. Let's switch to this. If I subtract a plus b plus c plus d equals 1 from the second equation, then I get 7a plus 3b plus c equals 5 minus 1 equals 4. If I do the third equation minus the first, I get 26a plus 8b plus 2c equals 14 minus 1 is 13. And if I do fourth equation minus first, I get 63a plus 15b plus 4c minus c is 3c equals 30 minus 1 is 29. Okay, we can work with this. And then from here, I guess I can multiply the first equation by 2 and subtract it from the second. So if I do 26a plus 8b plus 2c equals 13, and I do 2 times this, so 14a plus 6b plus 2c equals 2 times 4 is 8. Let me check, did I do everything right? 26, 8, 2, 13 is good, and 14, 6, 2, 8 also looks good. Subtract those from each other. 13 minus 8 gives me 5. The c's are eliminated, and I've got 26a minus 14a is 12a, and then 8b plus or minus 6b is 2b, so plus 2b equals 5. That works. And now I want to take this equation with this one, and I'm going to multiply the first equation by 3 this time to eliminate the 3c. So 63a plus 15b plus 3c equals 29, and 3 times this, so that's going to be 21a plus 9b plus 3c equals 3 times 4 is 12. Let me double check my math. 3 times 7, 21. 3 times 3 is 9. 3 times 1 is 3. 3 times 4 is 12. And did I copy the third equation correctly? 63, 15, 3, 29. Yep, we're all good to go. Mistakes here are very critical, so sorry if I'm being a bit paranoid. 42a plus 15 minus 9 is 6b. 3c minus 3c is gone, and 29 minus 12 is 17. Okay, and now put these two equations together. I'm going to multiply this one by 3 and subtract it from this one. So that's going to be 36a plus 6b equals 3 times 5 is 15. Okay, 42 minus 36 is 6a minus nothing equals 17 minus 15 equals 2. So a equals 2 over 6 equals 1/3. We've got our first value. Now we can plug it in to find b. Let's switch colors. I'm going to plug it in here. So 1/3 times 12. So I'm going to get 12 times 1/3 plus 2b is equal to 5. 12 times 1/3 is 4 plus 2b equals 5. Subtract 4 on both sides. 2b equals 1. Divide by 2, b equals 1/2. Okay, so that's our second value. Now plug into, I guess I'll plug it into here. To find c. So 7 times 1/3 plus 3 times 1/2 plus c is equal to 4. I'm going to multiply everything by 6 to clear the fractions. So 7 times 1/3 times 6, that's going to be, 1/3 times 6 is going to be 2. So 2 times 7 is 14. Plus 3 times 1/2 times 6. 1/2 times 6 is 3, so 3 times 3 is 9. Plus 6 times c is equal to, I multiplied everything by 6, so that would be 24. Okay, 14 plus 9 is 23. 23 subtracted from, hold on, 23 plus 6c equals 24. And let me double check my math. So we multiplied everything by 6. 6 times 4, 24. 6c. 18 times a half is 9. And 42 divided by 3 is 14. Okay, that all checks out. Subtract 23, and I get 6c is equal to 1. C is equal to 1/6. This does look like the right number. And finally, we need to solve for d. We had a plus b plus c plus d equals 1. So a plus b plus c plus d equals 1, and d should come out to be 0. Let's see, 1/3 plus 1/2 plus c equals 1/6. Yep, plus d equals 1. 1/3 and 1/6 is 1/2, and 1/2 and 1/2 is 1. So 1 plus d equals 1, d equals 0. Okay, so we got d equals 0 the hard way. But now we actually have our formula. Now we have a, b, c, and d. So let's go ahead and rewrite this formula. We've got a was 1/3. I'm looking at my other paper. The sum from I equals 1 to n of I squared is equal to 1/3 n cubed, 1/3 n cubed, plus 1/2 n squared, plus 1/6 n. And we can condense this into an expression that kind of looks like this. We can condense it even further. So I think that's actually what we want to do to try and simplify this for our next step. Let me think. Do I want to do that? Yeah, let's do that. Because I've seen usually the way that we do this Riemann sum is in the other form of this sum. So let's see what we can do to simplify this expression. Going back to this page over here, and let's switch to another color. I already used purple a lot. How about some orange? Actually, I might be able to start it up here. So we had 1/3, 1/2, 1/6, 1/3 n cubed plus 1/2 n squared plus 1/6 n. Let's see how we can simplify this. I guess I can start by factoring out a 1/6 n from these two terms. I'm not even sure if I'm on the right track here, but might as well learn. 1/6 n if I factor it out of these two. So let me actually group them first. So 1/3 n cubed plus 1/6 n plus 1/2 n squared. Let's group these by factoring out 1/6 and 1/6 n rather, and that will give me n over 6 times. If I take 1/6 out of 1/3, then that leaves me with 2 n squared, and then that should just be plus 1. Plus 1/2 n squared. Well, the 2n squared plus 1 does look familiar. So I think I'm on the right track here. And then, what do I want to do with this now? If I... maybe if I factor a 1/2 out of it? No, hold on. 2n squared plus 1 in parentheses, that's all good. That's something I was expecting to see. How do I deal with this now? Would it work if I rewrote this? Let's try n over 6 times 2n squared plus 1 plus 3 over 6 n squared. If I factor the 1/6 out of that, then I've got 1/6 all times n times 2n squared plus 1 plus 3n squared. No, that doesn't look right. Let me take a peek at what the actual sum is supposed to be. Okay, so what I'm supposed to be getting, and I do want to work on trying to get this, what I'm supposed to be getting is n times n plus 1 times 2n plus 1 over 6. This is what I'm supposed to be getting. Which means I probably screwed up somewhere over here. Okay, let's try this again. I think I want to start over from here and factor the 1/6 out of all the terms. Let's try and do that. Oh boy, I wasn't expecting this detour to take this long. I mean, I was expecting it to be long, but this is bordering on the ridiculous. Take out a 1/6 n, so take out n over 6, or maybe I just need to take out the 1/6. We'll see. Take out a 1/6 n, and you're left with taking 1/6 out of 1/3 leaves you with 2 n squared plus 1 plus, taking out 1/6 from 1/2, that's 1/2 divided by 1/6 is 1/2 times 6, which is 3n. I think I actually want to keep the n in there. Actually, no, wait, no. I don't need to keep the n in there because I have to have an n on the outside. So actually what I want to do is factor this. Yeah, hold on. I think I've got it. N over 6 times 2n squared. I'm going to rewrite it as plus 3n plus 1. And if I factor this, n over 6 times, let's see, this is going to be 2n and something, and then n plus something else. Factors of 1 are just 1 and 1, and if I do plus 1 here and plus 1 here, there we go. N times 1 is n plus 2n times 1. That's n plus 2n equals 3n. Okay, we got it. I was only slightly off. I just got a little too ambitious when I saw 2n squared plus 1 coming up. Okay, problem solved. So now we have it. Now we can go and come up with the formula for the integral of the x squared function, specifically if you're starting from 0. Specifically if you're starting from 0. The area under the curve for this thing as n approaches infinity. Let's go ahead and see what we can do with this. So area equals, it'll be the limit as n approaches infinity of delta x cubed times the sum from 1 to n of I squared, which equals the limit as n approaches infinity of delta x cubed. Do I want to FOIL that, or not FOIL, do I want to expand that now? Do I want to rewrite it as b minus a over n? I think I might as well. I think I might as well write it as b minus a over n, the whole thing cubed, times this sum as n approaches infinity. Well, it doesn't even matter what n approaches. It's always going to be n over 6 times 2n plus 1 times n plus 1. So n 2n plus 1 n plus 1 all over 6 as n approaches infinity. Okay, and I can see the n's are going to deal with each other as n approaches infinity. Maybe I should have actually kept it in this form after all. But yeah, we're going to get b minus a all cubed divided by 6. All of that I can factor out because it doesn't depend on n. So equals b minus a quantity cubed, which I have a feeling I'm going to have to expand later, all over 6 times limit as n approaches infinity of n times 2n plus 1 times n plus 1 all over n cubed. Right, that's what I get out of this. I get the b minus a all cubed in the numerator, and in the denominator I get an n cubed. Well, I can go ahead and reduce one of the n's, so now it's n squared. And if I put this back together, it should be 2n squared plus 3n plus 1. So that's limit, wait, I'm not going to have enough space for it here. Let's move on to a new sheet. So I'm going to flip back and forth a couple times to copy everything down. B minus a cubed over 6 times the limit as n approaches infinity of, we had n squared in the denominator, and then in the numerator we had 2n plus 1 times n plus 1, which foils to 2n squared plus 3n plus 1. 2n squared plus 3n plus 1. 2n squared plus 3n plus 1. And if I go ahead and distribute this n squared, essentially, then what I have is b minus a cubed over 6 times limit as n approaches infinity of 2n squared over n squared is just 2, plus 3n over n squared is 3 over n, plus 1 over n squared. Limit of a constant is just that constant is just 2. 3 over n as n approaches infinity. This approaches 0. Let me mark that with a different color. So this goes to 0. And 1 over n squared as n goes to infinity. This also goes to 0. So you're just left with a 2. So 2 over 6 gets you 1/3 times b minus a cubed, right? 2 times b minus a cubed over 6. That all works out. And then we want to do, well, a is 0 for our original problem, which was this over here. We should be getting 9 from this. So a is 0, b is 3, a equals 0, b equals 3, and I feel like there's something wrong with this, but I can't quite put my finger on it. I might have to put a pinned comment regarding this later, because something about this looks wrong. I have the feeling that it should be b cubed minus a cubed, not b minus a all cubed. I feel like I'm missing something here. I feel like I screwed something up. But a being equal to 0 saves it. So anyway, if I plug in a equals 0 and b equals 3, I get 1/3 of 3 minus 0 cubed equals 1/3 of 27 equals, what do you know? It is 9. The area is equal to 9, just as I said all the way back here. So there you go. That's, I guess, more of a calculus lesson than a physics lesson, but the physics-related stuff is coming. So I think I actually am at a good stopping point for today. The next time I cover this topic, because there is a continuation to this topic, I want to show off how Riemann sums can be used to calculate things more than just area. I think that will be especially relevant for physics students. I'm going to show stuff that's less directly tied to physics at first, and maybe for those of you who have had some physics before, those of you who've had physics 1, I might show off a couple of things you can do with physics without too much focus, and I'll focus on them more in depth once I get to those chapters in my AP Physics streams. But that is where we will have to call it a day, because I am quite frankly exhausted and I don't think I have the energy to keep going on. Hopefully this has been helpful. Let me know if there's anything you want to see, if you have any questions for next time, and yeah, enjoy the rest of your weekend, what little remains of it, and take care, and I'll see you next week.